Hi everybody, we are starting the 17th session of Ulpas and this session topic is sustainability. In this session, we have two invited speech. One speech will be made by Professor Mohammad JAWAID and second one from Dr. Aminoddin Haji. Dear JAWAID, are you here? Okay, we are starting second invited speech with Dr. Aminoddin Haji. His presentation topic is recent advances in sustainable dyeing of textiles. Can you show short biography of Dr. Aminoddin Haji? Okay, Dr. Aminoddin Haji obtained his PhD, Master Science and Bachelor degrees from Amir Kabir University of Technology, Tehran, Iran. He was working as a lecturer and assistant professor in Islamic Azad University in Iran. Dr. Haji is presently working as an assistant professor in Yazd University. His area of interest is surface modification of textiles, natural and synthetic dyeing of textiles, and nanotechnology in textiles and wastewater treatment. He has already published 66 papers in international journals, 7 book chapters, and presented more than 55 papers in international conferences. His H index is 20 in Scopus and 25 in Google Scholar. And now, if you are ready, we can listen to Dr. Aminoddin Haji.
Good morning, ladies and gentlemen. I'm very happy to be here. I would like to thank all the organizers of the conference, especially Professor Ali Demir for inviting me to this congress. My presentation is about the recent advances in sustainable dyeing of textiles. My name is Aminoddin Haji from Textile Engineering Department of Yazd University. Which one is the previous? Ready? Okay. I would like to have a brief description about my city and my university. At first, as you see in the map at the left corner, Yazd is a city located in the center of Iran. Its weather is normally a little high. It reaches 40 degrees in summer times. Today it is around 30 degrees, a little higher than here. And the weather is normally dry most of the times. Yazd University is a young university. it has about 35 years. Yaz University has more than 14,000 students, about 500 faculty members, and about 500 international students, and more than 50,000 students have been graduated from Yaz University until now. In Textile Engineering Department, we have 3 academic groups: Textile Chemistry, Textile Technology, and Clothing. And we accept the students at all levels of masters at BSc, MSc, and PhD levels. It does not work. Again. No, it needs battery. Can you change the battery? Please. So I can start with an introduction, and we will wait for the battery. As you know, the conventional textile dyeing processes have several problems. The consumption of huge amounts of water and the consequent environmental pollution are the most important challenges in the textile dyeing industry. For example, in the dyeing, finishing of cotton, dyeing and finishing of cotton as one of the most important textile fibers, around 125 liters of water is consumed per kilogram of cotton fibers. It is a huge amount. Furthermore, huge amount of energy is consumed for heating of the water and steam in dye houses. And the current inefficient dyeing procedures cause the loss of huge amounts of dye which remain in the dye baths after the dyeing. 60 to 80% of all dyes are azo dyes. And as you know, some azo dyes are carcinogenic. You will do it? Okay. As you know, some azo dyes are carcinogenic, and it is important to reduce amount of the carcinogenic dyes in the wastewater. Please change the slide. Go to next slide. Here you can see that in wool dyeing, with wool, nylon, and silk dyeing, with acid and mordant dyes, about up to 10% of the dye remains in the wastewater. For acrylic dyeing with basic dyes, up to 5% of the dye remains in the wastewater. For dispersed dyes, about 10%. But for cotton dyeing with direct dyes, the amount is higher, up to 30%, for reactive dyeing up to 50%, and for the sulfur dyeing up to 40%, and also for wet dyeing up to 20%. We can see that the huge amount of the dyes remaining in the dye bath of cotton dyeing may cause several problems. In the next table, you can see the parameters of a normal cotton dyeing wastewater: high pH, high COD, high BOD, high TOC, and this necessitates new approaches for dyeing, new approaches for pre-treatment before dyeing. Next slide, please. And also, some approaches are considered for the treatment of the previously mentioned wastewater. Biological methods, chemical methods, adsorption, membrane filtration, advanced oxidation processes, plasma treatment, and other processes are normally considered. Maybe more than one process, 2 or 3 processes in a row may be applied to treat the wastewater. But are these processes sustainable? They need additional costs, and maybe they may be not efficient despite the cost for the process. The next slide. Next, please. Okay. The alternative approaches are listed in this slide. We are looking for new and cost-effective and resource-efficient and sustainable dyeing alternatives to reduce the amount of carcinogenic compounds in the wastewaters. One approach is to reduce the water usage. For example, to use non-aqueous solvents like protic ionic liquids. The other approach is to replace the wasteful procedures with efficient and cost-effective ones, such as using supercritical carbon dioxide dyeing. Some pre-treatments are considered to enhance the dyeability of textiles. For example, cationization of cotton is one of the important procedures considered for improvement of cotton dyeing. And another approach is to replace the synthetic dyes with new and sustainable alternatives, such as natural dyes obtained from plants, or especially obtained from microbial pigments. Next slide, please. So we start with one of the approaches, which is waterless dyeing. Supercritical dyeing is gaining new attention in textile industry these days. As you know, in the traditional aqueous dyeing processes, large amounts of water are consumed, and the wastewater has to be discharged to the environment. And due to the increasing environmental awareness, waterless dyeing technologies have received enormous attention in the textile industry. One of such technologies is non-aqueous solvent medium, or NASM dyeing. Supercritical carbon dioxide dyeing is a NASM candidate suitable for dyeing of some kinds of textiles. Up to today, it is under development right now. As you know, when enough heat is applied to a solid, it begins melting, and liquid and vapor phases are formed. there is a critical temperature and pressure at which the vapor-liquid equilibrium line ends. I mean the point number 2 in this figure. When the pressure and temperature of the fluid is above its critical point, point number 2, it cannot be regarded as a liquid or vapor, and it is referred to as a supercritical fluid. The phenomenon shown in this figure is the supercritical charge of carbon dioxide. Carbon dioxide is the most widely used supercritical fluid in textile industry because it is inflammable, recyclable, and non-toxic, and has a relatively mild critical point and low price. The critical point of carbon dioxide occurs, as can be seen in this figure, at the temperature of 31 and the pressure of 7.38 megapascal. In dyeing, the supercritical carbon dioxide is heated up to 120 degrees Celsius and pressurized up to 250 bar. The dye molecules dissolve in supercritical carbon dioxide very easily, even more than in water. The CO2 penetrates the synthetic fibers very well, and thereby acting as a swelling agent during the dyeing and enhancing the diffusion of dyes into the fibers. Using the supercritical carbon dioxide in the textile dyeing has several advantages over the conventional aqueous dyeing methods, which include energy saving, because no drying is required, recycling of the carbon dioxide and the remaining dyes. Approximately no water and no pollution and no after treatment is needed. Also, this process is highly efficient and energy saving. Next slide, please. Okay. It can be seen in this slide that in a traditional dyeing, in several stages, wastewaters are produced. But in the supercritical dioxide dyeing, no wastewater is produced. At all stages, the CO2 can be recycled, even the dyes can be recycled and reused. So this process is very clean. Next. Yes, I know. It is, these days it is expensive because it is at the beginning, but maybe the technology will solve this problem later. Yes. Here you can see the samples dyed by supercritical carbon dioxide, and the staining on multi-fiber fabric is good. So the fastness is not a problem here. The fastness is good. Also, these samples show that this figure shows that the samples dyed using supercritical carbon dioxide with the same concentration of the dye are absorbing considerably more dyes, and the color strength is higher for the samples dyed by carbon dioxide. I will tell in the next slide. Next slide, please. Okay. The first question may be that is this technology at present at the industrial scale or not? Dyco, which is located in Netherlands, is the first company that produces carbon dioxide, supercritical carbon dioxide dyeing systems at industrial scale. It is consisted of 3 vessels that can be seen here. So you will purchase the 3 vessels at the same time. They sell all. Yes, as I told earlier, at this time it is expensive. But if you consider the benefits, the savings in energy, the saving in the dye, and the saving for the environment, it will be reasonable to work on this technology, to improve this technology for the future. This company claims that their technology uses 0 water, no processed chemicals, no wastewater is produced, 95% of the carbon dioxide can be recovered. So the price, only 5% of CO2 is consumed, is repelled to the environment. So you pay only for 5% of the solvent. 95% is recovered. It may be cheaper than a huge amount of water. And you use 50% less dye stuff to obtain the same color strengths. It is energy efficient, and the process cost is lower by 40 to 60%. The initial investment is considerably higher, but the process cost is lower. And it is now available on industrial scale. Next, please. Some well-known companies like Nike, Adidas, IKEA, and more companies are using this technology for the dyeing of their products. And the Dyco company is working in collaboration with some well-known dye producing companies, such as Colortex, Dystar, Acroma, Huntsman, to develop suitable dye stuffs. Okay. This short movie showed the working principle of supercritical carbon dioxide dyeing machine. As you can see, the pressurized carbon dioxide dissolves the hydrophobic dyes well. So it means that this process cannot be used these days for the dyeing of, for example, cotton with hydrophilic dyes. It is a problem that should be overcome in the next developments. So the dyeing of polyester or nylon or acrylic, for example, with dispersed dyes can be done easily by these equipments. They are easily dissolved in the supercritical fluid. The fluid easily penetrates and swells the fiber. The dyeing is very uniform. The process is highly efficient. And at the end of the process, by reducing the pressure, the solvent will turn again to gas, and the remaining dye will settle. There will be no wastewater. There will be no need for any treatment after the dyeing, no washing, no drying, and the fabric can be used for the next stage right after the dyeing. And the solvent can be recovered, the dye can be recovered, and it is very efficient. The next slide will show it. It is approximately equal or less than the conventional dyeing, because the conventional dyeing is time consuming. These companies are working with Daiku to develop new dyes, to be able to dye every kind of fiber using this technology. And it will be successful very soon. Next slide, please. Another company that is working on this technology is HK Rita. It is located in Japan. They have the same claims, and their equipment is not completely produced for industrial scale, but they are on the road to develop it for the industrial scale. The next process for the sustainable dyeing of textiles is the cationization of cotton. As you know, in the traditional cotton dyeing, a large amount of salt is used for the successful dyeing process. For example, you can see here that cotton fiber possesses negative charge, which repels the anionic dye molecules. All the dyes used for cotton carry negative charge. So there is a repulsion between the dye and the fiber. The salt is used to reduce the negative charge of the fiber so that the color, the dye molecule can be absorbed on the fiber and color the fiber. If we change the negative charge of cotton to a positive charge, I mean the cationization of cotton, then there will be no need for the salt, which is one of the most important problems in cotton dyeing. So, cationization of cotton has a versatile chemistry, and many processes which are conventional in textile industry can be used for the cationization of cotton. This process can be done by exhaustion, by cold pad batch, by pad steam, by pad dry cure, and combinations of these processes. It can be applied on any kind of cotton substrate in the form of fiber, yarn, or fabric. There is no need for salt. Up to 100% of the dye can be absorbed on the cationized cotton fibers. And the use of the consumables, such as energy, water, and steam, is considerably reduced, and overall cost savings are possible, and the amount of the used dye stuff is reduced as well. Here you can see samples dyed by conventional reactive dyeing and cationic reactive dyeing. I mean that the fibers, cotton fibers, have been cationized at first and then dyed using a conventional reactive dyeing. You can see that all the cationic cotton dyed samples have higher color strengths compared with the conventionally dyed samples, but the amount of consumed dye is considerably lower. You can see that about maybe half dye has been consumed to obtain a higher color strength. And here you can see that approximately there is no color remained in the dye bath after the dyeing of the cationized cotton. At least two general mechanisms are used for the cationization of cotton. One of them is shown here, and the other one and the other one is like this process. Here, in both processes, cationic chemicals are used. However, the difference here is that there is a radical polymerization process and a cationic compound with double bond is used. So, as I told you, the cationization can be done at every stage of the textile processing. Fibers and yarns can be cationized, knits and wovens as well. Many companies are producing cationized cotton goods, and Dow Chemical is selling some chemicals that you can buy and you cationise your own cotton. Okay, one simple process that we are working on it these days in our laboratory is the using of cationic starch in the dyeing of cotton. It is very cheap compared to some cationic substances. I have done several studies on application of Chitosan on cotton, on wool, on other fibers for the improvement of their dyeability and also their antibacterial property. Several papers have been published, but recently we started to replace the Chitosan with a very cheaper chemical to obtain the similar results. Cationic starch is very cheaper than Chitosan and carries a permanent positive charge. Chitosan is not permanently positively charged. It is positive only at acidic medium. So it's expensive and needs acidic medium to be positively charged, to improve the dyeing, to be antibacterial. But cationic starch is every time it is positive. You can see that cotton has been dyed with a direct dye. All are dyed with the same concentration of a direct dye. Without salt, the color strength is very low. By addition of 10% salt, the color strength is good, but only with 0.5% up to 2% of the cationic starch, the color strength is very similar to the sample dyed with 10% of salt. Here is the color strength diagram that I skipped. Another process that can be used for the more sustainable textile processes is plasma treatment technology. As you know, plasma treatment has been done in two distinct conditions, low pressure and atmospheric pressure. There are many companies in the world producing machinery for plasma treatment of textiles, for low pressure equipments, atmospheric pressure equipments. There are two examples, but there are many other companies. I skip more explanation. Next, please. Okay. I would like to explain very briefly only two of my studies in this field. For example, plasma treatment is very effective in improving the dyeability of wool fiber because the surface of wool is hydrophobic. It is coated with hydrophobic scales. And plasma treatment can make chemical and physical changes on the surface of wool. Both type of changes, chemical changes and the physical changes, I mean etching. You can see, it can be seen that the surface of wool has been etched after the plasma treatment. The chemical groups created after plasma treatment depend on the nature of the gas used during the treatment. For example, if you use oxygen as the processing gas, the surface of wool be more rich in oxygen containing groups, which may be beneficial for the dyeing of the wool in the next stage. Also, removal of the surface lipid layer improves the penetration of the dye molecules into the fiber. Here you can see by increasing the plasma treatment time, by increasing the power and increasing the oxygen flow rate, the color strengths of the samples have been increased. This was one of our previous studies. This is another one. Here we used Chitosan after the plasma treatment. I mean that the surface of fiber was activated by plasma, then it was coated with Chitosan, and the color strength was significantly improved to be more eco-friendly, to be more sustainable. We used the natural dyes for this process. You can see here that the dye uptake was increased. W means the fiber's wool, raw wool, no process. P means the plasma treated sample, and PC means the plasma treated and Chitosan coated sample. It can be seen that dye uptake as well as the dye fixation has been increased after the plasma treatment and also after the Chitosan coat. Another alternative approach is the use of biocolorants. It can be plant-derived colorants or even the microbial colorants. You know that natural dyes are obtained from plants, from some animals, and also from microorganisms. Maybe someone tell that for obtaining the natural dyes, you should destroy the nature, you should destroy some plants. But if you use microorganisms, nothing is consumed, no plant is consumed. And there are some companies working on producing on microorganism produced natural dye, like the Faber Futures bacterial pigment extract produced by a UK-based laboratory. Another approach to prevent the use of toxic dye substances is the structural coloration. The formation of structural colors is a visual perception. It means that no actual dye molecule is used. So this process is dye-free. no dye is used, and fadeless. You know that most of the dye molecules are weak against light. If the substrate is structurally colored, I mean, for example, by some nanoparticles, you know that, for example, silver nanoparticles, depending on the size of the particles, are normally gray or brown. Other nanoparticles, depending on their shape, on their size, on their shape, may exhibit different hues, different tones. So structural coloration is a good or new approach for coloration of textile without using any dye molecule. Also, many of the nanoparticles exhibit additional properties. For example, antibacterial, anti-ultraviolet, and etc. Next, please. Sorry, previous one. Okay, this is the last slide. There are some other technologies provided by some companies, for example, air dye or NTX cool trans, that are based on some kind of transfer printing. Foam dyeing is another process. Dope dyeing is an alternative in dope dyeing. No chemical, no water, no auxiliary is used, but it has some problems. Professor Demir will know everything about it because he is working in this. But it is an approach to eliminate the use of excess water, many other chemicals. Also, microwave heating, ultrasonic processing are other approaches that are normally used these days in the research studies, also in industry. They can improve the dyeability of fibers and reduce the time, the consumption of chemicals, and also the energy. And in conclusion, I can say that the textile industry consumes huge amounts of water and different types of dyes and chemicals, which makes it one of the most polluting industries in the world. To minimize the water consumption and avoid repelling such a large quantity of dyes and chemicals into the environment, development and application of more environmentally friendly processes is necessary. Waterless dyeing, as well as the suitable pretreatments and eco-friendly dye alternatives are among the most widely studied methods for overcoming this problem. Thank you for your attention. This is one of the historic places, one of the touristic attractions of our city, Yazd. The name is Amir Chakhmar. I invite all of you to visit Iran, especially our beautiful city, historic city, Yazd. I hope to meet you next time in Iran. Thank you very much.
Conference, and then we may join.
I hope.
Thank you, Dr. Haji, for your presentation. Is there any question to Dr. Haji? Okay, I think, yes, I think important questions were asking during the presentation.
Aminuddin, you have made a very thorough presentation summarizing all those possibilities. I would like to ask your personal opinion. Which one would you choose if you were at the critical point?
As a researcher, I have a long experience on plasma treatment and coating after plasma treatment. On natural dyeing, I prefer a combination of these two processes. These days, I'm working on the dyeing of synthetic fibers with natural dye. Also, I think that there is a great potential for the supercritical dyeing. one of my colleagues from Turkey, Dr. Hossein Akselere, who has supercritical laboratory dyeing machine. We are working. Hossein Akselere. Yes, I know. He's some equipment, and currently we are working on a project jointly for the dyeing of polyester, for the dyeing of cotton with natural dyes. The initial results are not too bad and are not very good, but hopefully we will try to improve the results. Thank you.
Okay, I want to give you your certificate. Now we are, Dr. JAWAID, are you here?
Yes, brother, I'm here.
Okay, if you are ready, we can listen you, Dr. JAWAID. Our second invited speech is starting. Okay, Dr. JAWAID, you can start. Oh, sorry. Firstly, I introduce Mohammad JAWAID. He's a professor at Putra, Malaysia University, and has been visiting professor at King's South University. He has more than 20 years of experience in teaching, research, and industries. His area of research interest includes hybrid composites, nitrocellulosic, reinforced fluid polymer composite, advanced material. And so far, he has published 55 books, 75 book chapters, and more than 400 peer-reviewed international journal papers, and several published review papers under top highly cited articles in Science Dyeing. Recently, Dr. Mohammad JAWAID received excellent academic award in category of International Grant University Putra, Malaysia, and also excellent academic staff award in Industry High Impact Network award. He also received Pablo's peer reviews awards 2017 and 2018. Certified Sentinel of Science Award recipient in 2016 and 2019. Now today he will make his invited speech presentation. Okay, we are waiting for you, Dr. JAWAID.
Please able me to share the screen. Disable from there.
Okay, you can share now.
Okay, my screen is visible to you?
Yes, JAWAID, we can see it.
Okay. Bismillahirrahmanirrahim. Assalamu alaikum, and good morning and good afternoon to the people as per the time in your place. So today, basically, I'm going to talk about one of the research carried out by one of my students to develop the what you call the bulletproof jacket by using a coconut sheet. So basically today my presentation is the coconut, Cocos nucifera, botanical name, sheet-based composite for ballistic applications. So before going on to that one, I just give you the brief introductions about my university. University Putra, Malaysia is one of the research-based university in Malaysia, and they have a very big campus, around 3,000 hectare land. And we have offering 156 degree programs, 15 faculties, 11 institute, 2 school, and 1 academic. And we have also different international ranking, and we have the faculties and all these things, and we have also the higher education center for excellence. And we have also the different accreditations, academic accreditation worldwide. And we have also the collaboration with different university, including the Istanbul Technical University. These are some activities, clusters, and innovations and commercialization in various fields done in case of the fertilizers or vaccines, and all these things are there. And some of them are presently commercialized. And this is the different organizational award, and all these things are there. And this is the industry linkage with that. So this is the few information. This is my student group. It's almost before the lockdown, and some of them already graduate, and some of them are still working with me. So basically, this is the guy you're looking with the French, Naveen. He's basically presently assistant professor in India. So he done this work. So basically today we are going to talk about the introduction, natural fiber. If the people do not understand the natural fiber, hybrid composite, and hybrid composite for ballistic applications, and problems and objective methodology, what we done. And basically we are going to talk about what we developed from this work. So basically, as everybody know that the natural fiber the fiber have divided into the two parts: natural fiber, synthetic fiber. The natural fiber, there are different sources: animal and minerals and plant, and the other side synthetic, there is organic and inorganic, and they have the different classification as per the availability. And this is, if you look into natural fiber, this look like that: dead palm, abaca, quiet. This is the plants which look like that one before extracting the fibers. When you extract the fiber, different type of fibers you get in the different form. And if you look into the chemical compositions of the natural fiber, the three things is common: cellulose, hemicellulose, and lignin. And it can vary from the type of the natural fibers. If you look into the jute, flax, rami, hemp, which are the lignocellulosic bast fiber, they have better cellulosic content as compared to the other natural fibers, and it gives the better strength for applications. And there is a physical properties. As we know, the density, the lighter material, heavy materials, accordingly, we can use it for different applications. And also on the basis of length, diameters, and microfibril angle, they will play an important role when you are going to design any product from it. This is the classification of composite. When you are going to make a composite, as we know that the composite materials are classified on the basis of the matrix. It means metal, ceramic, and polymer-based composite, we say. And within that one, we have also divided into the fibrous, particulate, and laminates. And then we have the natural or biofibers, or we have the synthetic fiber. Within the synthetic fiber and biofiber, there is also the biofiber. If you use the biopolymer, we call the biopolymer composite, and the biofibers plastic composites. And when you combine the two fibers or two polymers, you blend it, they call it the hybrid composite. So hybrid is a general word. It's found into the numerous science field, and it's provide a superior and combined properties compared to the monolithic composite from the single fiber or single polymers. And it have been the different hybrid composite as two or more reinforcing phase embedded into the single continuous phase or single reinforcing phase embedded with the two or more matrix in there. So these are the different applications you can do in automotive, defense, aerospace, packaging, wind turbine blade constructions, and others. So these are the different applications of the composite. It can be into the construction, can be in automotive, and can be into the ballistic applications. So when we are talking about the ballistic, there are multifunction material consists of two or more chemically constant, and fiber reinforced composite, as we know, that widely used into the aerospace, automotive, and defense applications. And when we are talking about the fabrics using outstanding mechanical properties and ballistic resistance are used in the ballistic structures and in protecting the clothing. So there are three types of structure. One is called body armor, vest, helmet, and protective shield. So recently, as you know, the natural fibers are getting, due to environmental awareness and environmental regulations from the governments, people are coming to replace the man-made synthetic fibers. And the natural fiber modified can be found in efficient and convenient way to improve the properties of the fiber reinforced polycomposites. And most commonly used nanofillers, we are using the nanofiller, CNT, GNP, and different types of nanoclay and all these things. So in this research, we basically hybridize the Kevlar with the natural fiber. Together, the modifications with the graphene nanoplatelet will provide superior property for protective application. So first, we try to look into the literature. We find out that the people have already done the work on Kevlar, Kenaf, and others, but nobody have reported any works on the Kevlar with the Coccus nucifera sheets. So we try to study that one, and also we modify the resins by using a GNP, and we try the different properties. And as we know that the problem that degradations and non-biodegradability of petroleum materials and all these things, and environmental global warmings and all these things, pushing people to use the natural fibers materials. So in this study, basically that we have first tried to find that suitable material natural fiber. Is it really the Coccus nucifera is a good natural fiber for ballistic application or not? And then we have examined the hybridizing the Coccus nucifera sheet with the Kevlars and modification with the GNP, and we studied the mechanical properties, physical property, morphological properties, and structural properties of all these things. And we also studied the ballistic performance before GNP, and then after that also the modified by the GNP. Also we studied the thermal properties and dynamic mechanical properties. So this is the what we call as the a flow chart of that one, how and which type of the testing we mostly follow the ASTM standard, but in case of the ballistic testing, it's NIJ standard 0108.01 is acceptable. So we use this in this study. And as you saw that this is the Coccus nucifera and its morphological properties here. And the right side, you look into the Kevlar fabrics are there. And this is the SEM image of the graphene nanoplatelets. And we have different types of setup and formulations for the laminated composite. We do the different layering patterns, and we have varied the Kevlar and Coccus nucifera sequence and all these things. And you look at dispersion, because as you know that when you are going to put the nanoparticles, you need to have tactically how to disperse the nanoparticle properly. Otherwise, agglomeration will going to happen. And this is the setup formulation for the ballistic gun testing. That is the ballistic testing into the room setup by using a gun. And if we go that one, as we say that one, first we use the analytical Haji process for body armor application. And we look the different natural fibers, that who is the best fibers on the basis of different criteria set for the ballistic. That one, the cellulose density, tensile strength, young modulus, cost, and availability have taken that one. And we have done the different analysis by using a software, and be able to get the conclusion from that one, from the sensitivity analysis. It has been found that among the 7 criteria, except tensile strength and tensile modulus, the remaining 5 criteria show that the Coccus nucifera sheet is the most promising natural material for hybridizing with the Kevlar 29 for body armor applications. Therefore, we utilize in this study the Coccus nucifera. And we done the different studies on hybridizing the coconut with the Kevlars. We studied the tensile properties, we studied the flexural properties, impact properties, and all these things. But due to limitation of the time, this all work have published, so you will get the more information on this one on the online. So we find out that one, the hybrid, because individually we look into that one, that what you call that coir-based composites have mechanical properties wise, the hybridized one have played the better properties in form of tensile property, flexural properties, or impact properties. And this is the fracture samples we taken from that one, and we analyze that, how this happens, and what are the interfacial bondings and all these things between the fiber and matrix. And we also studied the effect of hybridization on water absorption properties, and we have also studied the crystallinity index of different laminate after the hybridization. And we have also studied the energy absorptions of the laminated composite. But when it saw that one, when it's in the case of the energy absorption, you look into the S5, which is the pure coconut epoxy, have better, because due to the white content and the pore within the coconut fabrics. And this is the failed sample with the damage profiles. We have analyzed that, how much the damage happened due to the gunfire. And we have also studied the effect of the GNP on energy absorptions of laminate. So if we find out that there is a, in case of that, because we use the two combinations, 0.25 and we use 0.5 weight, because as you know, the GNP is very costly in the that one. So we need to control the what you call the costing of the materials. So we find out that one, there is not much changes we get from the GNP in these composites. And we have also analyzed the projectile after the ballistic impact. And just a moment. Screen is not moving. Yeah. So then we have also studied the thermal. Oh, sorry. It's already, just a moment. It's stuck for the time being, and when I click, it's gone. Just a moment. Sorry, just a minute. That's, I don't know, it's a hang or something happened. So I'm just again coming back with that. Okay, so we done the mechanical properties on the basis of the what you call as the impact laminates, and then we also done with the flexural and impact properties on the effect of GNP on the ILSS. So if you look into that one, very few places the 0.25 show the better interlaminar strength, and in case of the S2, it show that what you call the G3, which is 0.75 is better in case of the flexural modulus, and in case of the flexural strength, you saw that 0.25 is showing the better. So it's not the similar result in all the properties we are getting from this one. And we have evaluated the morphological studies, and we try to link between that one. So all the details is already published. So you can find out the full papers are available at the internet. And then we have also analyzed that one, the effect of aerial density on the ballistic performance, ballistic limit of the composites, and we have looked into the specific energy absorptions of the laminated composites with the 9-layer and 12 layers. So we find out there is a very slight difference. We find out into the specific energy absorption in case of the 9-layer and 12-layer, especially in the case of the coconut nucifera-based composites and the hybrid composites. And this is the failed sample with damage profile. And we have also studied the effect of GNP on the ballistic limits of the composites. And we find out that one, even without GNP, is showing the better results. Only in case of the 12 S11, it show that what you call the 0.25% is better. Otherwise, most of them, the GNP effect, we don't find out much in the case of the ballistic applications. And we also studied the thermal analysis of that one. And also we have studied the dynamic mechanical analysis of that one. So as you know that the thermal analysis is that what we call as a loss of the weight with the temperatures. And in case of the dynamic mechanical analysis, you will look the properties, mechanical properties with the temperature. In that you have stiffness and what we call as the storage modulus, loss modulus, and tan delta. You get out that one. So you look that because initially the material is in the solid form, but when you you will increase the temperature. It started to go towards the glassy region, and then they started to rubbery region, that one. And the movement of the particle within the composite have started to move, that one. And we have also done the loss modulus, and we have done the tan delta is the ratio between the storage modulus and that one. And Cole plots is basically draw to know that one, the material is homogeneous or heterogeneous. And we have plotted here that the major degradation temperature, final temperature, and char residue in the case of the different composite. This paper published into the polymers, and there is a major degradation, initial degradations, and all these things have narrated there. And also we started same thing in the dynamic mechanical analysis of the effect of GNP on the loss modulus and effect of GNP on the storage modulus. And similar thing we studied on the effect of GNP on the damping plots, the tan delta of the laminates of the different layerings and the different types of composite, the pure composite and hybrid composites. And we concluded from this study that as first objective that the Coccus nucifera was identified the potential material for armor application, and we find out that the mechanical properties improve the mechanical and moisture behaviors due to dispersion of the GNP, enhance the mechanical interlocking, and also the high ballistic performance of the hybrid and Coccus nucifera sheet reinforced is attribute to randomly interlaced dense weaving natures of the Coccus nucifera. And also we find out that as earlier showed that the addition of GNP slightly improved the ballistic performance of the Kevlar fabric reinforced. And we have from the thermal analysis and all these things, we find out that can effectively replace the Kevlar at elevated temperatures. And additions of GNP improve the thermal stability and viscoelastic properties of the laminated composite. And Kevlar can be efficiently replaced with the Coccus nucifera sheet at an optimal GNP loading of 0.75. So from their analysis study, we done the one prototype from that, and the prototype we tested with the live bullet, that we done in that one, and we put the product name is the techno-economic hard body armor. And we have go through the invention, what type of invention. This is a base multi-layer hard body armor system which protect the shoulders against the high kinetic energy particles, 7.62 mm calibers according to the NIG level 3 standard at 840 to 850 meter per second. The velocity is there. And we have what is the unique is this one. This existing Kevlar based multi-layer armor system is costlier and it pollute the environment after serving, but the natural fiber based hard body armor reduce the environmental issues and the cost. And we propose that one because that is the trauma level is 26 mm is in our case, which is the standard is the 44 mm. So our case is that one, less than that one. So we pass that under the standard. And we have that the proposed body armors contain the ceramic, composite, metallic layers, and ceramic is well known for the ballistic application. Second, composite layer absorb the dissipated and kinetic energy, and this is the further stop the impact energy. And during the ballistic testing, according to the NIJ 01010 standards, the multi-layer armor panel was fixed over a Roma plastina block. Is a type of a what you call that the body, and it can be fired with that 7.62 mm live bullet. And the clay witness the stimulate the human body being secured by the multi-layer armor, and they should carry the shock wave up to the standard backface signature limit up to 44 mm. And the ballistic trauma, as I say, that 26.51, and the limit is 54. And we also find that our armor, which we are making from the Coccus nucifera, will save the 44% of the fabrication cost. And research have proved that the Coccus nucifera sheet can be a most promising alternative to the Kevlar fabrics. And this is the environmental issues and other thing I'm not discussing. So this is the flow chart of preparing the multi-layer body armor. And we done the testing, ballistic testing, and we also analyzed the blunt trauma measurement and analysis of the result. And this is the live setup of in the Defense Center in Malaysia. We done the live bullet testing here. Multi-layer armor is there, and this is the bullet caliber for that one. And this is the tested samples after the live bullet testing. And after that, we check the indentations and to check the depth of the indentation. So we find out that our back-facing natures is less than that. We have in case of the Kevlar 24, our case in the focus is 26, and both have a partial penetrations and is passed as per the NIJ standards. And this is, we analyze the costing and we find out that it will around 44.43% the cost effectiveness if you are going to make a bulletproof jacket by using a focus lucifera sheet. And this is another patent people have done. So we try to compare with that one. So earlier the patent people have done hard body composite, including a rigid non-ceramic facing and ballistic fabric backing. There is another patent on the US, is inductive body armor. Our case is related to the field of fabrication, agro-based hard body armor. And this is a multi-layer armor composite of ceramic plate, focus lucifera, and aluminum alloy. Other is non-ceramic facing, glass, carbon, graphite, ballistic fabric backing, expect that. And this invention is I have one aspect of the placement of the personal protective hard and industry application, defense sector, of course, all are in the defense sector. This is the what called the photograph of the existing patented one, the current technology, an outline of the claim and all this thing. I'm not going. And this is the some of the when we make that one, it's come into the news. First started from the my university portal, and after that it covered by the different newspapers in Malaysia. So this is some of the what called the media coverage. I'm showing here you body armor made from the part of coconut tree. UPM researcher created the bulletproof armor from the coconut. Then this Malaysian researcher came up with the coconut-based armors. This is the what you call another paper covering that one. So there are different media coverage done on this one. So anybody have interested to know more about that one and all these things, so we will later on share the informations with all of you if you are interested to work in this area. And I'm thankful to my PhD student, Dr. Naveen Jesu, who carry out this work during his PhD. And I'm also thankful to the funders, University Putra Malaysia, Ministry of Higher Education of Malaysia for HICO Fund for 6369108. And I'm also thankful to Prof. Dimir, Ali Klik, and other team member for inviting me for the 10th ULPS 2022 for sharing my idea. Thank you so much. And this is my email ID. So if anybody want to communicate with me, please communicate, writing the email to me. So discuss further on that. Thank you so much.
Thank you for your presentation, Professor JAWAID. Is there any question to Professor JAWAID? Dear JAWAID, our time is very limited. I think questions can be sent to you after.
Yeah, no issue. Just I share my email ID. So anybody want to ask any question, they can email to me. Okay.
Okay. Thank you so much, dear JAWAID. See you next Ulpas, inshallah.
Inshallah. Thank you so much.
Okay, we can continue with sponsored presentation. Karafiber
Herkese merhabalar. Ben Kubilay Özden. 2,5 yıl önce intern mühendisi olarak girdiğim Karafiber Tekstil'de Ar-Ge merkezinde Ar-Ge mühendisi olarak çalışıyorum. Tekstil mühendisiyim. Aynı zamanda Gaziantep Üniversitesi'nde yüksek lisans yapıyorum. Karafiber 1989 yılında %100 yerli sermaye ile Gaziantep'te 275 bin metrekare kapalı alanda üretim yapmaktadır. Bizler 2000'den fazla nitelikli çalışanımızla birlikte 2000'den fazla nitelikli çalışanımızla birlikte iplik, örgü kumaş, boyanlı tesislerimizle entegre tekstil ve layosel elyaf tesisimizle tam entegre tekstil halinde hizmet vermekteyiz. Ayrıca enerji sektöründe, nonwoven sektöründe ve streç film sektörlerinde de üretimlerimiz devam etmektedir. Bizleri ticarette Selçuk İplik olarak tanıyor olabilirsiniz. Biz bir yıl önce isim değişikliğine gittik. İlk 500 sanayi firması arasında 211. sırada, tekstil kategorisinde de 9. sırada yer almaktayız. 1989 yılında Open İplik eğilme tesisiyle başlayan işletmemiz 2010 yılına kadar tekstil işletme sayılarını arttırarak sektörde lider firmalar arasında kendisine yer almaktadır. 2011 yılından itibaren diğer sektörlere giriş yapan kara fiber, enerji sektöründe ve streç film sektörüne de giriş yapmıştır. Her zaman ilkleri hedefleyen kara fiber, 2013 yılında Türkiye'de ilk olan A-Late Nonwoven tesis üretimini faaliyete geçirdi. İlerleyen yıllarda üretimlerini arttırdıktan sonra 2021 yılında Türkiye'de ilk ve tek olan layosel elyaf üretim tesisine başladı. Her zaman kurulduğu yıldan itibaren üretim kapasitesini ve cirosunu arttırmayı hedefleyen kara fiber tekstil bu hedeflerini gerçekleştirme yönünde ilerliyor. İngiltere, İspanya, Portekiz, Amerika başta olmak üzere Afrika'dan Avrupa'ya, Uzak Doğu'dan Amerika'ya birçok ülkeye ihracat yapmaktayız. Kara fiber tekstil olarak 5 farklı sektörde 16 işletmemizde günlük 350 ton üretim kapasitesine sahibiz. 3 farklı iplik eğilme tesisimizle %100 üretim, ekru karışımlı üretimler ve melaj karışımlı üretimler yapıyoruz. Boyane işletmemizde elyaf boyama, kumaş boyama gerçekleşiyor. Nonwoven tesislerimizde ise 3 hattan oluşan A-Late ve Spanlace hatlarımız bulunmakta. Ambalaj sektöründe ise streç film üretiyoruz. Ve son olarak da elyaf tesisimizde ekolojik ve selüloz kelimelerini ifade eden Ekosel markamızda layosel elyaf tesisimiz kuruldu. Ekosel markası dediğim gibi Türkiye'de ilk layosel elyaf üretimi. İlk aşamada şu anda yıllık 25 bin ton üretim almaktayız ve bu yılın sonunda bu hedefimizi 2 katına çıkaracağız. Layosel elyaf üretim süreci kuru jet ve ıslak eğirme işlemleriyle gerçekleşmektedir. Şekilde de gördüğünüz üzere endüstriyel ortamlarda yetişmiş ağaçlardan elde edilen odun hamurunu alıyoruz ve doğal çözgen olan aminooksit grubundan N-metil morfolin N-oksit içerisine çözerek çözdükten sonra bu elyafımızı çekme germe işlemlerinden sonra saf su içerisinde yıkıyoruz. Daha sonra elyafı tov haline geldikten sonra saf su içerisinde yıkadıktan sonra kesme işlemleri gerçekleştiriliyor. Kesme işlemlerinden sonra elyaf açma ve balyalama işlemiyle layosel elyaf üretimi tamamlanıyor. Daire içerisine almış olduğumuz kısımdan bahsedecek olursam, bu sistemi çevreci kılan nokta sürdürülebilirlik çatısı altında bu bahsettiğim doğal çözgeni biz N-metil morfolin N-oksiti işletmede %99.6 oranında geri kazanıyoruz. Ve bu da bu sistemin çevreci olmasını sağlıyor. Bu tek bir slide üzerinde anlatmış olduğum sistem 50 bin metrekarelik tesiste bulunmaktadır. Ve continuous bir sistem olmasından dolayı herhangi bir hatayla karşılaşıldığında sistem durarak kendisini koruma altına almaktadır. En az işçilikle yürütülen fabrikamızdır. Ekosel yüksek mukavemetli, parlak, yumuşaklığıyla ipeksi dokunuşa sahip ve doğada parçalanabilmesiyle çevreci bir elyafdır. Burada da tabloda da gördüğünüz üzere kalite değerlerimiz mevcuttur. Ekosel elyafı, Lyocell elyafı rejenere selülozik elyaf grubuna yer aldığından dolayı diğer rejenere selülozik elyaf gruplarından modal ve viskon elyafıyla karşılaştırdığımızda Lyocell elyafına bir fiziksel çözünme mevcuttur. Ama diğer iki gruptaki elyafta kimyasal çözünme mevcut. Ve proses zamanı olarak incelediğimizde Lyocell elyafını biz 2 ila 4 saat, maksimum 6 saat arasında üretiyorken diğer elyaflar 35 ila 48 saat aralığında üretilmektedir. Ekosel elyafının biz eğirme hızı 60 metre bölü dakika ile 300 metre bölü dakika aralığındadır. Diğer elyaflarda bunlar daha kısa, daha uzundur. Çözücü olarak kullanıldığında diğer iki modal ve viskonda zararlı olan C2S kullanılmakla birlikte bizlerde kullandığımız doğal çözgen olan N-metil morfolin N-oksit ile çevreci bir elyaf üretiyoruz. Modal ve viskon üretiminde kullanılan kimyasaldan kaynaklı ortama çıkan sülfür gazı insana ve doğaya zararlı olduğundan dolayı birçok yerde sınırlı üretime sahiptir. Odun hamurundan elde ettiğimiz Lyocell elyafı tekstil alanında giyimden ev tekstiline kadar birçok alanda kullanılabilmektedir. Sürdürülebilirlik hedeflerimiz altında kara fiber olarak karbon ayak izi ölçülmesi ve azaltılmasına yönelik aksiyonlar alıyor ve her yıl sürdürülebilirlik raporu ile açıklıyoruz bu durumu. Global bir marka haline gelerek firma projelerimize sıfır atık yolunda her zaman ilerliyoruz. 2016 yılında 17 hedef çatısı altında yayınlanan sürdürülebilirlik hedeflerinde Ekosel markamızla diğer üretim tesislerimizde ürettiğimiz ürünlerle ve Ar-Ge projelerimiz doğrultusunda bu amaç doğrultusunda her zaman kara fiber olarak ilerliyoruz. 6 lisans üstü araştırmacı, 20 lisans mezunu araştırmacıyla birlikte 2018 yılının Şubat ayında Sanayi ve Teknoloji Bakanlığı'nın onayıyla Ar-Ge merkezimiz kurulmuştur. Ve bu geçtiğimiz yıl 2,5 milyon TL harcama gerçekleştirdi Ar-Ge merkezimiz. 2 adet tamamlanmış 1501 projemiz, TÜBİTAK 1501 projemiz, 23 adet öz kaynak projesi, Horizon başvurumuzla birlikte bu projelerin çıktısı olarak 6 adet patent ve faydalı modelimiz var. 21 adet marka tescilimiz, 8 adet ulusal ve uluslararası dergilerde makale, 26 adet ulusal ve uluslararası kongrelerde bildiri yayınlayarak bilime katkıda bulunuyoruz. Ar-Ge projelerimize her zaman yenilikçi Nonwoven kompozit ürünler tasarlayarak yeni markalar elde ediyoruz. Sprayco, Carlate ve Airlace markalarımızla birlikte ek olarak iplik üretimlerimizde Vortex iplik eğirme sisteminde özlü iplik üretimi ve geri dönüştürülmüş polyester üreterek Vorpet markamızla ürün portföyümüzü geliştiriyoruz. Ambalaj sektöründe çevreci olmasından dolayı çevreci olarak masurasız streç film üreterek Ecorlus markamızla piyasada streç üretiyoruz. Yeni ve sürdürülebilir elyaf gruplarının iplik ve örme kumaş olarak üretimlerin yapılmasını her zaman Ar-Ge projelerimizde de destekliyoruz. Ar-Ge projelerinde stratejilerimiz incelendiğinde yüksek katma değerli, verimliliğin arttırılması, enerji ve su kullanımının azaltılması, geri dönüştürülmüş ham madde kullanarak çevre dostu ürünleri geliştirerek atık miktarının azaltıcı önlemlerin sağlanmasıyla birlikte Ekosel markası gibi yeni dünya markalarını geliştirmeyi her zaman stratejilerimiz arasındadır. Bizlere ulaşmak isterseniz iletişim adreslerimiz bu şekildedir ve standımız açıktır. Teşekkür ederim beni dinlediğiniz için.
Sponsor firmamıza sunumu için ve Ulpas'a katkıları için teşekkür ediyoruz.
Biz teşekkür ederiz. Sağ olun. Bu güzel etkinlik için.
Hocam buyurun.
Buyurun hocam.
Üretiminde kullandığınız su miktarı ne kadar?
Su miktarı şu anda yani bir saf su kullandığımızdan dolayı yüksek miktarda tonajlı üretimden dolayı bayağı bir kullanıyoruz suyu ve o zaten suyu geri dönüştürüyoruz biz. Onu her zaman
Yani kullandığınız su miktarı ne kadar biliyor musun?
Su miktarını reçete bazında bilemiyorum açıkçası. Onu işletme kapalı bir sistem olduğundan dolayı.
Peki kullandığınız su miktarı için bilgin var mı?
Efendim?
Kullandığınız su miktarı yani kilo başına ürettiğinizde ne kadar su harcıyorsunuz?
Dediğim gibi hocam bu sistemimiz kapalı bir sistem ve kapalı bir üretim olduğundan dolayı reçetelerimiz var. Reçete bilgim yok açıkçası.
Peki su tedariği nereden elde ediyorsunuz? Yeraltı
Kendi
suyu.
işletmemizden.
Yeraltı
Evet.
suyu.
Evet, yeraltı havuzlarımızdan.
Peki attığınız yani bir kısmını geri kazanıyorsunuz ama atıyorsunuz. Atıkları nereye deşarj ediyorsunuz?
Atıkları biz Gaziantep Organize Sanayi Bölgesi'nin bulunduğu bir bölgeye aktarıyoruz. Sanayi bölgesi de onları şey yapıyor daha sonrasında. Yani bütün işletmelerimizde biz o atık suyu dediğimiz gibi toplayarak birleştiriyoruz. Bu şekilde hocam.
Şimdi biliyorsunuz bu üretimde bol miktarda su kullanılıyor.
Evet.
Dolayısıyla yani su sarfiyatını geri kazandığınızda yüzde kaçını geri kazanıyorsunuz?
Yüzde şöyle söyleyebilirim hocam. Biz o bütün üretimlerimize, Nonwoven'da da yine bu tarz bir geri dönüşüm söz konusu. Nonwoven'da ve elyaf üretimlerimize bu %90 oranında, 95 oranında saf suyu geri kazanıyoruz işletmemize. Geri kalan kısmını da biz bahsettiğim gibi gönderiyoruz suyu.
Peki, teşekkür ederim.
Ben teşekkür ederim hocam. Sağ olun. Tabii ki.
Son dönemde markaların özellikle beklentileri arasında ve önümüzdeki yıllarında stratejik planlamaları doğrultusunda aslında konvansiyonel elyaflardan çıkıp sürdürülebilir elyaflara yönelimiyle ilgili beklentileri var üreticilerden de.
Evet.
Bu kapsamda ekosel elyafınızda izlenebilirlik kayıtlarını, izlenebilirlik takibini sağlayabiliyor musunuz?
Tabii ki. Ekosel kapsamında dediğiniz gibi hem izlenilebilirlikleri sağlıyoruz ve markalaşma yönümüzdeki bu sertifikalandırma süreçlerimiz devam etmektedir. Bu konuda sıkıntımız yok yani.
Yani süreç şu an halihazırda devam ediyor ama
Evet, süreç
sertifikalandırma yani bugün ben ekoselle çalışmak
birçok sertifikamız var zaten. Özellikle PALT kullandığımız için FSC sertifikamız var. Diğer sertifikalandırma süreçlerimiz de devam etmekte.
Elyaf izlenebilirliği özelinde ben sormak
İzlenilebilirlik konusunda da şeyimiz var zaten. O konuda sıkıntımız yok.
Peki bir de yine beklentilerden birisi de Green Canopy sertifikaları veya işte denetiminde yine green olmasını bekliyorlar elyaf üreticilerinin.
Doğrudur.
Bu konuda Kara Fiber
Bu
hangi
konuda-
aşamada?
Bu konuda da çalışmalarımız sürdürülebilirlik ekibimizle birlikte devam ediyor her zaman. Şu anda
Yani green short seviyesine geldi mi ya da işte şu an hangi seviyede onunla ilgili bir bilginiz var mı?
seviye konusunda bilgim yok. Yani hangi aşamada yüzdelik olarak veremiyorum. Bilgim yok o konuda ama şöyle söyleyebilirim sizlere. Sürdürülebilirlik ekibimiz sürekli bu Ecosel markasıyla ilgili çalışmaları üstüne bastırarak devam ediyor. Ben teşekkür ederim. Sağ olun. Teşekkürler. Sağ olun.
Okay, now we are continue with oral presentations. Dr. Mehrizi will make his presentations. His presentation titles are A Study on Production of Biofuel from Textile Waste as a Feedstock and Electrospun Carbon Fiber Composites for Water Treatment. He will make two presentations. And now I want to introduce Mohammad Khajeh Mehrizi to you. He received his PhD degree from Isfahan University of Technology. He is currently teaching at Yas University as an associate professor. He has published about 45 journal papers. His main research interests are surface modification of textile, printing and dyeing of textiles with natural dyes and the correlation of textile effluents. Now he is starting his presentation.
In the name of God, good noon, ladies and gentlemen. I will be thanks from organizing team, and my study is about the production of biofuel from textile waste as a feedstock. At the first, I want to explain the importance of energy. According to the international agency, the world will need more than 37% in 2040. The progress has been fundamental in the using of non-renewable energy sources, comprising coal about to 29%, natural gas about 24%, and oil 37%. And today, fossil fuels are dominating the global energy market. Fossil fuels are non-renewable with limited reserves and the high prices that cause climate change, emission of greenhouse gases, environmental pollution, and damage of biodiversity. With growing concern about fossil fuels, biofuel as an environmental friendly energy source has received a large amount of attention in recent years. Biofuel are fuels derived from biomass, which can play an essential role in reducing greenhouse gas emission. The biofuel are we can produce biofuel from the waste textile. Biofuel are divided into the 3 generations. The first generation is the biofuel from sugar and animal fat. You can see the corn and soybean in this table. And the second generation is related to in the biofuel from numerous kind of vegetables like jatropha and castor. And the last generation is related to from microalgae and microbes. You can see in this table the production from third generation is the best method for generation of biofuel. We can take biofuel from text-based from 30 method. At the first, we can produce biofuel from cotton-based waste textile, and then we can take from sludge waste, and the last we can produce biofuel from leather fleshing waste. The textile manufacturing process a significant amount of solid waste, according to Environmental Protection Agency report 2030. Annually, 50.1 million tons of textile waste is generated from USA. Waste textile management is the using of second-hand textile, filling materials, landfilling, and burning. All of these processes have negatively impact on the environment and lead to the loss of energy and raw material. Therefore, it is essential to develop a technology to reuse non-toxic organic and biomass to produce of renewable energy. But about the cotton-based textile, population growth has been one of the critical factors to more energy and fiber consumption. Around 40% of the fiber consumption in the world is cellulose. Almost 1/3 of waste textile from clothing and other textile products are cotton and viscose. Cotton textile industries face critical problems on waste management, which result in environmental pollution and health hazards. If you look at the picture, you can see the waste from different steps in cotton processing. It can be shown that waste of spinning process like carding waste, combine oil, and sweeping waste and microdust. And about weaving process, the waste conclude fiber waste and yarn waste. We can produce biofuel from textile waste, from jean waste and cotton waste. For the various processes involved in biofuel production include pretreatment, hydrolyze, fermentation, and distillation. We want to talk about the pretreatment process. One of the major challenge in biofuel production from waste textile is highly compact and crystalline structure of cotton, resulting in very low bioconversion rate and yield. Thus, a suitable pretreatment is required to improve the digestibility of cotton-based waste textile and achieve a high yield of biofuel production. The pretreatment, like chemical and physical and biological method, is considered as one of the most staged for destroying the lignin and increase the amorph region. And the next step is hydrolyze. The hydrolyze of the biomass is conversion of polymers such as cellulose, hemicellulose, and lignin into monomers such as reducing sugar like glucose. And then we go to fermentation step. Fermentation is the bioconversion of monomer like reducing sugar to biofuels such as bioethanol. And the last, we have distillation step. Distillation is necessary for the separation of bioethanol from raw products. You can see some study about production of biofuel from cotton. At the first, you can see the study of Hassanzadeh and et al. In 2080. They use the waste gene include 40 section polyester and 60% is cotton, and they use alkaline treatment using sodium carbonate with different condition with 0.75 and 1 molar at 150 centigrade for 2 hours. And you can see the most of ester yield was about 50%. You can see the sample B3, and the treatment was with 1 molar sodium carbonate at 150 centigrade. And Jane Hantour at et al. In a study and this process at 2009, and they use waste gene and cotton, and they use pretreatment with sodium hydroxide 12% and 0 centigrade for 30 hours, and enzymatic hydrolyze at 47 centigrade for 24 hours. And you can see the highest bioethanol yield was about 86%. And the second step for production of biofuel from waste textile is sewage sludge. Sewage sludge is a byproduct of process involved with wastewater treatment. With the rapid increase in industrial activities, large amounts of sewage sludge are generated annually. For example, in 2018, Taiwan's industry produced more than 1.1 million tons of biological sludge. Composition of textile sludge is heavy metal, dye, and a substantial amount of organic matter, phosphorus, nitrogen, and micronutrients. Several sludge can be used for soil improver or phytoremediation process. Phosphorus and nitrogen content in sewage sludge improve the organic matter of the solid structure. The sludge is a potential source of lipid up to 30% based on dry sludge that could be used as a source of cheap and available for biofuel. For production of biofuel, we can use 3 steps. At the first, pre-treatment with ultrasonic and mechanical disintegration, and the second step is lipid extraction with some solvent like hexane and chloroform, and the last step is transesterification for production of biofuel. You can see the reaction between triglyceride with alcohol in the presence of sodium hydroxide as catalyst. Manucci et al. In 2080 produced bioethanol from sewage sludge. High bioethanol yield were obtained at an incubation period of 10 days. Bioethanol production from sewage sludge is a treatment-sensitive process because the process has biological nature, and high temperature are a stress factor for microorganisms. Also, the yeast is denatured and reduce the bioethanol yield. You can see the figure, and they show the sensitivity of temperature and pH to the gain the bioethanol concentration. High bioethanol yield were obtained and incubation in the temperature at 30 centigrade and pH 6.5 with the yeast of 6%. And the last method for biofuel production conclude the leather felation waste. Tanning industry is a major source of pollution, and tannery wastewater is a potential environmental concern. The leather industry uses skin as a raw material, which are the byproduct of meat and felation waste. The waste generation from the tannery process is estimated over 6 million tons annually. The leather felation waste generated from the tanneries cause environmental impacts such as groundwater contamination and color problems. The method of wastewater treatment such as chemical coagulant, biodegradation, absorption, and reverse osmosis cause high consumption of energy, the need for a large area of land, and high cost. One way to recover the leather waste is using them as feedstock in biodiesel production due to their rich fatty acid content. You can see the type of fatty acid from flaxseed oil, such as stearic acid, oleic, and another one. And you can see the reaction between fatty acid and alcohol in the presence of acid as catalyst. We can attain the methyl ester for biofuel. And the end, the addition of high amount of catalyst leads to formation of an emulsion and the gel. This hinder and the glycerol separation and reduce the ester yield. And Krishna and et al. Use tannin refrigeration base to produce methyl ester via trans-esterification. The highest methyl ester content, about 89%, was obtained in 30 hours reaction time at 65 centigrade and 1% of catalyst and sodium hydroxide as catalyst. And then the annual production of textile waste is increasing, causing an increasing concern regarding the impact of disposal of waste on the environment. The conversion of waste to reusable product is gaining much importance in today's world. Generally, textile waste like cotton waste, sewage sludge, and leather fleshing can potentially be used as sustainable feedstock for biofuel production due to availability and high amount of cellulose and fat. The production of biofuel from waste textile could be possible from different materials with and without pretreatment. The pretreatment helps to open up the structure of material and make it easier for the microorganisms to degrade it. Thus, the use of waste could be a viable, economically and environmentally alternative for the produce of energy. And you can see the some reference. Thanks a lot for your attention.
I think you can continue with other presentation.
Yes.
Okay.
Could you believe from secondary? Thank you. Thank you very much. And another article is about the Electrospun carbon nanofiber composites for water treatment. This study is divided into the 4 parts. The first part is the introduction about the Electrospun carbon nanofiber, and the next step is related to the experimental, and then we go to result discussion and the conclusion. We have conclusion. Carbon nanofiber as CNFS have been applied as dispersion for absorption of organic pollutants such organic dyes, solvent, and volatile organic compounds such as benzene. However, application of such dispersion is limited by the practical consideration, like potential for material release. Application of CNFS composites has focused in energy applications such as supercapacitors and battery anodes rather than sorption of polar and or polyfunctional organic micropollutant. To improve CNF strength, several groups have evaluated the effect of embedding CNTS within the nanofiber. Embedded CNTS are commonly utilized to improve both mechanical strength and electrical or thermal properties of polymeric nanofiber. And about carbon nanofiber as filtration material, carbon nanofiber have attracted considerable attention in the field of water filtration as they exhibit unique features such as high porosity, large surface to volume ratio, low density, and high flexibility. The fiber-based membranes have a small pore size, low cost, and high efficiency in terms of the removal of contaminants from water, while the production of a free-standing non-polymeric nanofiber mat is still a technological challenge due to their intrinsic brittleness. Large area CNF sheets with high mechanical strength and flexibility can be easily fabricated. And we go to PAN and CNT for more effective than CNFS. Embedded CNTS in Electrospun hybrid PAN and CNTS nanofiber serve as nuclein centered in the PAN carbonizing process so as to provide for a more ordered graphic texture with enhanced crystallinity in the region adjacent to the CNT surface. Furthermore, as the embedded CNTS are usually well oriented along the fiber axis in Electrospun nanofiber, it is expected this process to result in enhanced orientation and crystallinity in the fabricated carbon nanofiber. Fassin et al. In 2040 studied about Electrospun carbon nanofiber membranes for filtration of nanoparticles from water. CNFS membranes were fabricated by the electrospinning of PAN processors solution followed by the thermal treatment of the Electrospun fiber. Additive was added to the polymer solution to increase the specific surface area of the CNF and to provide flexibility and mechanical strength needed to withstand filtration under pressure or vacuum. These developed filters were capable of efficiently rejecting nanoparticles of different size and nature, like AU, AG, and TiO2 from aqueous solution. The result described demonstrate the great potential of these membranes for the filtration of nanoparticles from water, mainly because of their tunable pore size, very high permeability, and ability to produce nanofibers in an easy and cost-effective way by electrospinning. Moreover, they can propose for the promising system recovery of valuable nanomaterial from complex matrix. You can see the producing filter without, you can see when we use this product, this Electrospun carbon nanofiber embedded with the nanoparticle, for example, IU nanoparticle, the concentration of the absorbance of the effluent was reduced, and dislike for using the AG nanoparticle with this filter, and you can see with using the AG nanoparticle with different diameter from 10 nanometers to 60 nanometers, the filtration efficiency was around more than 99%. In this study, all reagents were used as received polyacrylonitrile. We use polyacrylonitrile with the molecular weight of 150 and DMF with from the DBH chemical and multiple carbon nanotube with the about 8 nanometer diameter we use. And sorption experimental were conducted in 5 millimolar phosphate buffer prepared from deionized water and pH adjusted as needed with 5 molar sodium hydroxide. And preparing nanofiber for CNF mat, 8% pans was dissolved in DMF by mixing at 60 centigrade for 2 hours. For multiple carbon nanotube embedded CNF mat, non-functional CNTS with different percent 0.8 and 1.6 and 2% relative to total soil gel mats were first dispersed in DMF via ultrasonication for 5 hours. Prior to dissolution of pan in multi-wall carbon nanotube DMF suspension. Electrospinning were done with a 12 milliliter plastic syringe. And we finally prepared the CNFS. After electrospinning, thermal oxidative stabilization was most often carried out for 2 hours at 280 centigrade in air. The mat was returned to room temperature prior to pyrolysis for 1 hour at 1000 centigrade in an N2 atmospheric. And you can see the different morphology of Electrospun nanofiber. A sample is unmodified fibers, only pans, and B only CFS. And B is CNF with 0.8% CNT, and C sample is related to CNF embedded with 2% CNT. The average fiber diameter were developed from measurement of 50 to 100 nanofiber in MAG software. You can see the figure. The average diameter of unmodified nanofiber was around 160 nanometer, but when we embedded with CNT about 0.8%, the average diameter was about 130 nanometers, and when we use 2% CNT for production of new filter, we have nanofiber about average diameter of 80 nanometers. And we have some experimental experiment to attain the efficiency of filter. Ulpas experiments utilize a piece of nonwoven mat. Initial sorbent optimization was conducted with atrazine. ATZ is abbreviated as atrazine, and sulfamethoxazole as SMDX, SMX, to identify the best sorbent material for spaces exhibiting a range of polarities. Equilibrium times were determined first via kinetic experiment. Kinetic experiment monitored the decrease in ATZ and SMX concentration over time in sorbent suspension at pH about was 7. You can see when we use the CNT with embedded with 2% CNT, the absorption was decreased, and it was same for SMX effluent. And when we use CNF without modified, and the concentration was constant in the different volume of effluent, but by using the CNF and CNT, you can see the reduce the concentration of effluent. And finally, we make combination treatment with the different sorbent like SDMX, SMX, and ATZ, and NPX, and BZF. In this simplified aquatic matrix, more than 95% removal was maintained after 3 of operation for naproxen and bezafibrate and gemizofibrate. This presents the 3 compound with the largest reported, but all 3 have deprotonated OH group under the condition of out-follow-through experiment. We propose the primary driver for their sorption is via hydrophobic interaction with the sorbent surface derived by non-polar moieties like aromatic ring in the structure. When examining performance toward less hydrophobic compound based on hydrophobic compound, the highest degree of removal was observed for the sulfa drug, include SDMX and SMX, with more than 90% removal observed for SDMX and complete background of SMX only after 3 liters of effluent volume. And then nanocarbon sorbent fabricated via electrospinning represent a significant practical advance in water treatment. The optimized CNF and CNT composite exhibit sorption kinetic much faster than those of commercially unmodified CNF. In this study, embedded CNT serve as the primary active sorbent in this material, and CNF-CNT composite may represent a self-contained platform through which the unique reactivity on CNT can be safely harnessed during water treatment while minimizing risk of their release into the finished supply. Thank you a lot, and I'm here to answer your question.
Thank you for your presentation. We couldn't able to take question, I think. Now I will want to give your certificate.
Take a photo. Tamam. Hocam sen şöyle. Tamam hocam, geliyorum. Buyurun, bunlar sizin.
Thanks a lot. Two cups. Thanks a lot.
Okay.
And I want to thank from organization team, and I like my friend Dr. Haji invite you to visit my city in Yaz in Iran. Thanks a lot.
Okay, we are continue with Dr. Aminoddin Haji. It's presentation topic ionic dye removal using polypropylene nonwoven functionalized by Chitosan, titanium dioxide and silver nanoparticles.
Okay, hello again. I know that the time is over, so I will skip some of the slides. The title of this presentation is the anionic dye removal using polypropylene nonwoven functionalized by Chitosan TiO2 and silver nanoparticles. Is it working or not? Please next. Okay. I will explain these slides very briefly. Here you can see the mechanism of interaction between the chitosan and anionic dyes. Chitosan gains positive charge in acidic media and can attract the anionic dyes. Next slide. Okay. Also, you know that titanium dioxide nanoparticles show photocatalytic activity. As well, the silver nanoparticles have the same photocatalytic activity, and it has a synergistic effect when used in combination with titanium dioxide. I added a small introduction for the polypropylene fiber, but I skipped it. Only I want to mention that polypropylene has no active group, and it is needed to modify its surface by some means of chemicals or like that. Here we use the plasma treatment to create oxygen containing groups on the surface of polypropylene and attach the chitosan on its surface. Then I skip the introduction of the materials used and in this study to save the time. We used a low pressure plasma equipment made in Iran for the oxygen argon treatment, plasma treatment of the samples before the coating with chitosan. Chitosan was applied by a pad and dry process. Then the titanium dioxide nanoparticles were applied using immersion under sonication and then drying process. Afterwards, the silver nanoparticles were synthesized on the surface of the treated samples in situ. I mean that there was no silver nanoparticles used. It was synthesized on the surface of the samples prepared by plasma, by chitosan, and then by titanium dioxide nanoparticles. We used an acid dye for this study. UV visible spectrophotometer was used for the measurement of the dye in the dye bus. And the photocatalytic activity was examined under UV radiation. FESEM and FTIR were used for the characterization of the samples. Here you can see the morphology of the raw polypropylene fibers and also the plasma treated fibers. You can see that etching took effect on the surface of the fibers due to the plasma treatment. Next one. Can you help? Okay. Here you can see that chitosan has been attached on the surface of the fiber, TiO2 nanoparticles, and the silver nanoparticles have been synthesized on the surface of the previously prepared sample. So, next please. Next. Okay. The Edx analysis confirms the presence of oxygen element on the plasma, on the surface of plasma treated sample. Here, the presence of nitrogen confirms the presence of chitosan on the surface, and we have titanium element and silver and titanium in these samples. All this data can be used to confirm the presence of the aforementioned elements on the surface of the prepared samples in different stages. The FTIR spectra confirmed the attachment of the materials on the surface of the nonwoven, and I skip the explanation. Here you can see the efficiency of the chitosan coated sample at different pH values. As you know, the chitosan gains the positive charge at acidic media, and this adsorbent showed the highest adsorption capacity at pH of 3. So this pH was used for the further studies. For the samples coated with different concentrations of titanium dioxide nanoparticles and tested under UV radiation, we can see that the removal efficiency increased for the samples coated by the titanium dioxide nanoparticles because it has photocatalytic activity. But comparing, next please. But comparing the different concentrations of titanium dioxide, we can see that by increasing the concentration of the titanium dioxide nanoparticles, the efficiency was decreasing because of the agglomeration of nanoparticles on the surface, which limits the accessibility of the nanoparticles for the dye molecules. Next, please. In this figure, we can see the effect of adding of silver nanoparticles on top of the prepared adsorbent. This step made a little difference, not too much, but silver nanoparticle can have a synergistic effect when used in combination with TiO2. Silver alone shows a weak photocatalytic activity. One advantage of adding the silver is that it shifts the adsorption of the TiO2, the photocatalytic region of TiO2 to visible range, not only in the UV range. So it means that by adding silver nanoparticles to the prepared composite adsorbent, it will show photocatalytic activity under visible light as well. And next, please. So in conclusion, sorry, because I skipped some information and some presentation due to the lack of time. In conclusion, we can say that the PP nonwoven, polypropylene nonwoven was functionalized by plasma, chitosan, TiO2, and silver nanoparticles, respectively. The ability of the modified samples for the removal of anionic dye from water was studied. The chitosan coated sample was able to remove about 90% of the dye at pH of 3. The application of titanium dioxide and silver nanoparticles on the surface of the sample enabled the adsorbent to degrade the dye molecules under UV radiation, and the dye removal efficiency was improved. I should say that the dye removal efficiency for the Chitosan coated polypropylene was not bad, but the dye molecules remain on the surface of the polypropylene, and it is another problem. But when you apply the photocatalyst on the surface, the dye molecules are degraded. So the adsorbent can be used repeatedly without any further process. It can be used again. The prepared photoactive adsorbent can be a good candidate for adsorptive and photocatalytic removal of anionic dyes from textile waste water. Thank you very much for your attention. Sorry. For which step? Okay. I agree with you. Yes, but if the polypropylene is very cheap compared with other substrate, we need a substrate to coat it or modify it with some chemicals. I agree with you that Chitosan is a little expensive, but the substrate is very cheap that it can cover the high cost. Cotton is more expensive than polypropylene. And the other one, yes, yes, I know. But cotton is biodegradable. It will be degraded after some usage, but the polypropylene lasts more. It can be used more times. Okay, thank you.
Another certificate.
Thank you.
Also, it is your another cup.
Thank you. Thank you.
Okay.
Thank you.
Our last presentation will made by Hülya Kıcık. His presentation title is New Generation Sustainable Fibers for Clothing. Hülya Hanım lisans ve yüksek lisans eğitimini Uludağ Üniversitesi Tekstil Mühendisliği bölümünde tamamlamıştır. Tekstilde 3 yıl üretim tecrübesinin ardından 7 yıl bir firmada Ar-Ge mühendisi olarak çalışmıştır. 3,5 yıldır da Elyaf Tekstil'de Ar-Ge müdürü olarak görev yapmaktadır. Sunumunu dinleyeceğiz şimdi. Buyurun. Soldaki, bir soldaki. Bir soldaki hocam. Evet, bir ölçün. Tamam.
Yazılar çok gözükmüyor ama başlıyorum. Thank you all for coming to listen my presentation. Today, I would like to share with you new generation sustainable fibers which are suitable for clothing industry. Before I start, I would like to quickly introduce my company. Elyaf Textile produces dyed printing woven fabrics for women's wear. It has about 400 employees and it is located in Bursa, Turkey. Its production capacity is 1 million meter per month. Elyaf Textile is an integrated facility. It has printing, it has twisting, warping, weaving, dyeing, printing, finishing and garment making departments. Our main customers are H&M and Inditex Group. Besides, we work with luxury fashion brands such as Banana Republic and Moschino. Here you can see examples of our fabrics. And in this page, you can see our certifications, verifications, and memberships. We are one of the most innovative company in Turkey. We won lots of awards from different platforms. Here you can see awards that we won. Turkey Textile Innovation League is one of them, and it changed its name as Textile Innovation League since 2020. And we also won award from 10th Chemistry R&D Brokerage event. And we are among top 500 companies by R&D expenditures in Turkey. As of May 2019, we have been entitled to receive R&D Center certificate by the Ministry of Industry and Technology and became an R&D center. And we run different R&D projects since then. And now we can talk about new generation sustainable fibers. According to the report published by Textile Exchange, global fiber production in 2020 is approximately 109 million meters. When we compare this report with the previous year data, we can easily see that there is an increase in the rates of recycled, bio-based, and organic products. While the sustainable cotton percentage was 25 in 2019, it became 30% in 2020. When we look FSC certified man-made cellulosic fibers rate, this rate increased from 40-50% to 55-60% in 2020. Also, we see increasing recycled polyester percentage. For this reason, it is obvious that fiber sustainability issues will gain importance in the future. I will mention sustainable fibers under the following 4 topics. Actually, there are more than 100 sustainable materials that we found, but I will tell you only 27 ones due to time limitation. Firstly, I will start with cellulosic virgin fibers. I will briefly talk about 4 different fibers under this topic. I will share related links at the end of the presentation. If you want to have more information about these fibers, you can use that link later. First fiber is orange fiber. Byproducts of citrus juice industry is used to produce sustainable orange fiber fabrics. Lansing and Orange Fiber collaborated and produced first Tencel limited edition branded lyocell fiber and made of orange pulp and wood sources. Another fiber is C-cell. It's produced by mixing cellulose obtained from sustainably managed forests with 8 to 10% seaweed. Next fiber is Spinova. It only mechanically refines the cellulose raw material using the developed technology, and it converts to ready-to-spin fiber without harmful chemicals. And naturally colored cotton. Such cotton fibers are inherently colored. Some kinds of cotton have various shades of green, brown, or pink. No need to dye fabric produced from this yarn, but yarn strength must be checked. And here you can see inherently colored cotton plant. Next topic is synthetic virgin fibers. I'm going to mention 6 different fibers in this category. First of them is alginate. It produces degradable synthetic yarns from kelp. Kelp is a type of seaweed or microalgae, which one of the most renewable organisms on the planet. Another yarn is corn leaf. It's a synthetic yarn produced from corn and contains the advantages of both natural and synthetic fibers. This fiber also known as PLA fiber in the sector. And the next polymer is polytrihydroxybutyrate. Polyhydroxyalkanoates, also known as PHA, are good examples of bacterial polyester. Mango Materials currently produces P3HB which is one member of the PHA family. Fermentation technology of mango materials produces a biopolymer from naturally occurring waste biogas. Next fiber is Amnisol Eco. It's a biodegradable polyamide 6.6 fiber that allows clothes to break down quickly when they thrown away and left in landfills. And another fiber from the same company is Evo. It's a bio-based polyamide yarn. The renewable biomass source of the produced yarn is obtained from castor oil plant called Reginus communis. I hope I pronounced it correctly. And another fiber is microsilk. In the microsilk production process, silk proteins spun by spiders are studied. Then proteins is being developed using bioengineering to insert genes into DES. Fermentation process is used for large-scale production. No spider kills during the process, and this fiber is biodegradable. I think this one is the most interesting one. And next topic is cellulosic recycled fibers. I will talk about 9 different fibers in this section, and AgroLoop is the first one. This product is produced using plant stems and leaves using existing spinning methods. TextLoop is another yarn of the same company. TextLoop recycling systems are designed to manage a variety of waste, including natural fibers, synthetic fibers, and its blends. Last yarn of the same company is Orbital Yarn. It is produced by using organic and recycled fibers with orbital spinning technology. Its spinning technology is different from the conventional yarn spinning, and it gives fibers fast drying property. Next fiber is Infinna. It uses new methods to produce fiber from used textile, cardboard, and agricultural waste. Another fiber is Liva Reviva. Liva Reviva is produced from 80% FSC certified wood pulp and 20% pre-consumer cotton fabric waste. And Circulose. Circulose is a branded dissolving pulp product that renews and makes from 100% textile waste, such as worn out jeans and production scraps. Another fiber is Recover. Circularity is ensured by converting post-consumer textile waste back into fibers. Another fiber is Borneva. Fabric scraps that occurred during the production of textiles and apparel are collected to produce Borneva fibers. As the textile produces Borneva yarn, and it is located in Turkey. Last fiber in this category is Naya Renew. Naya Renew structure contains 60% sustainably sourced wood pulp and 40% recycled waste plastic. Plastic wastes are converted to acetic acid used in acetate production. It's a different way to recycle, to produce recycled yarn. And last topic is about synthetic recycled fibers. There are 8 different fibers in this section, and first one is Q-Nova. Q-Nova fiber consists of yarn waste from the yarn production cycle, and it's mechanically recycled polyamide. This page is about recycled polyamide yarns, by the way. Another yarn is Econil. It is produced from recycling of finishing nets and carpets, recyclable and reproducible over and over again due to chemical recycling method. Another fiber is Nippon Regen by Hyosung. Is a recycled polyamide produced by recycling pre-consumer waste, and it's a mechanically recycled polyamide yarn. And this page is about recycled polyester yarns. Renew is the first one. Renew is a product that used pre-consumer and post-consumer polyester waste, and it is chemically recycled polyester. Another one is Regen. Region is made from 100% recycled material derived from post-consumer PET bottle waste. It is mechanically recycled polyester. Next one is Reprieve Our Ocean. It is specially obtained from plastic bottles collected from coastal areas close to the water with a high risk of going to the ocean. It's a kind of mechanically recycled polyester. And this page is about recycled elastan yarn. Roika is one of them. Roika reduces the environmental impact at every stage, from raw material section to the production process and the sale of elastan yarn. All cooling water, materials, equipment used during its production are recycled and reused at the rate of 99%. Next recycled elastan yarn is Lycra Ecomate. It helps to supply sustainable textile products for consumers by using 40% pre-consumer Lycra waste. Let's summarize this presentation. Fibers, their companies and countries are here. And if you want to get detailed information about these fibers, you can visit this website I shared. Orange this plus sign shows that it is commercially available. Orange fiber, alginate, P3HP, and microsilk are not commercially available yet. They are still under development for large-scale production. Here you can see sustainable cellulosic recycled fibers. All fibers are commercially available except Infinna fiber. And here there are sustainable synthetic fibers that I mentioned, and their companies, countries, and websites. All fibers can be found on the market in this category. Thanks for your listening. If you want to get in touch with me, you can use this email address and phone number. Thank you.
Thank you for your presentation. All presentations were completed for this session, and we are starting session 10. But first, I should give certificate. In session 10, we are starting with invited speech.